You now have a lot of strategies for solving integrals. Well, what if we take a function like 1 over x squared here, and we want to find the area of the curve to the right of 1. That means as we go to infinity here, so we're going to stretch this out infinitely long, so we have no boundary on the right. Well, what's going to happen to that area? Well, we have a horizontal asymptotes, right? And there's always going to be a little bit of a gap here. It's going to be pretty small. You can't see it pretty soon. But it's never really going to close. And we want to figure out, can we actually find the area as we go out to infinity? Let's explore this a little bit. So let's find the integral of 1 over x squared from 1 to b. Okay, so we might rewrite that as the integral of x and negative 2 dx. And if we add 1, we get x and negative 1 divided by negative 1. So we have negative 1 there. And that'll be from 1 to b. Okay. Plugging in b to figure out our definite integral here, we have negative 1 times b to the negative 1, which is negative 1 over b. And when you plug in 1, we get minus negative 1. All right? So we get negative 1 over b plus 1. Okay. So now the question is, what if we take that and take that integral from 1 over b and we crank that b up to infinity? See, if b was 2, so if we did the area from 1 to 2, then we would have negative 1 over 2 plus 1. That'd be a half. If we did the integral from 1 to 3, well, we'd have negative 1/3 plus 1. That would be 2/3. Okay? Well, let's find our limits here as b goes to infinity of this. Well, this is the limit as b goes to infinity of what we just found, which was negative 1 over b plus 1. And what happens to this fraction as b goes to infinity? Well, that fraction becomes 0, right? So we get 0 plus 1, which is obviously 1. Kind of interesting. So if we're looking for the area underneath the curve from 1 to the right, we get 1. Okay? So we see that the area continues growing, but we're always adding more and more as we go to the right. But eventually we add so much little that we get the total area. We can find the total area. We say it converges because the limit exists. Okay? If the limit doesn't exist, then we say that diverges. So if something doesn't exist, the limit doesn't exist, that diverges. Okay? Which will happen. We'll see. Let's check out some more. Okay? So first of all, before you check out this next one here, here's our little definition of a limit at infinity. So, or I should say an integral going to infinity. So if we want to find the integral and we have a bound that's at infinity, well, we have to rewrite that from a to b, and we say what is the limit as b goes to infinity. Okay? Or we can go the other way. If we got negative infinity on the left, we can rewrite this as an integral from a to b, and we're going to crank a down to negative infinity. All right, so this one looks the same. Let's check this out. Let's do the same thing. So we're going to rewrite this, the limit as b goes to infinity. So we're going to rewrite this as 1 to b of 1 over x, or we'll go ahead and rewrite this as x and negative 1. Okay. Well, what is the integral of 1 over x? Well, that is natural log, right? So the antiderivative of 1 over x is the natural log of x. And we're going to do this from 1 to b. Okay, so let's rewrite this. This is the limit as b goes to infinity. Okay, we're evaluating from b to 1 or 1 to b. And so we have the natural log of b minus the natural log of 1. Okay? Remember what the natural log of 1 is? Well, the natural log of 1 is 0, because what is the power you put on e to get 1? The power is 0. So this is the natural log of b. Well, as b goes to infinity, what is the natural log of b going to? Well, if we think about the graph of the natural log, so this is y equals the natural log of x, okay? It comes up like this, and it continues growing. So it's going to grow slowly, but it's going to always grow. It's always increasing. So the limit as b goes to infinity of natural log of b is infinity. Okay, there is no bound. Okay, so this diverges, we say. That means there is no boundary, all right? There's no limit. Okay, so it's a divergent integral here. We can't figure out what it actually is. So kind of interesting. It worked for 1 over x squared, but we cannot find the infinite integral of 1 over x. All right, on this one here, let's say we're going to negative infinity. All right, so we're going to rewrite this integral from 0, actually make that a to 0, of 1 over x squared plus 1 dx. And we're going to find the limit as a goes to negative infinity. Okay? All right. How do you integrate this? Can we use u substitution? Nope. Okay, can't use u substitution. Can we do integration by parts? I don't think that's going to help us. But do you recognize this form? This is inverse tangent, right, or arctangent. Okay, so it's arctangent straight up. We don't need to do any trig substitution there. This is just arctangent. So this is the limit as a goes to negative infinity of arctan of x from a to 0. All right, and that is going to be the limit. So we'll do the limit last. Keep copying the limit down here, all right? We've got arctan of 0 minus arctan of a. All right? For the parentheses maybe. So what is the arctangent of 0? We're asking ourselves, thinking unit circle if you want, or actually maybe even better yet, think of the graph. Do you know what the graph of tangent looks like? Might be a good one to kind of remember. Tangent, that's that one, looks like this. Okay, has some asymptotes here. What angle, what value of x will have a tangent of 0? So this is what angle has a tangent of 0? Well, the answer is 0. When the angle is 0, the tangent is 0. Okay, if we think unit circle, all right, unit circle, if we want tangent of our angle to be 0, that means sine over cosine is 0. So where on the unit circle is sine over cosine 0? Well, that happens when sine is 0, and sine is 0 at 0. Okay? And other multiples of that there, right? Okay, but arctangent is actually just defined. We're just going to define it from negative pi over 2 to pi over 2. Okay, so it is the limit as a goes to infinity. This, again, is 0. So this is going to be 0 minus, so that's negative arctan of a. Okay. So here's the function y equals tangent of x. Okay. The arctan function, if we take this middle part, so remember with the arctan function we have to limit the range. Okay. So if we take y equals arctan, let's look at that real quickly here. We get this, y equals arctan. And that graph is going to look like this. Okay? So it's just that middle one flipped over. Okay? So as x goes to negative infinity, what's happening to this y value? Well, it actually has a horizontal asymptote because it's this graph flipped over. What is that horizontal asymptote going to be? Well, it is pi over 2, negative pi over 2. All right, so this is negative pi over 2. Okay. All right, let's look at one more here. Okay, here we have an integral. This is going from negative infinity to infinity. So we're going to need to have left and right bounds. All right. So we need to break this up. So this, we're going to break it up. We're going to cut it off at 0. And so let's write this as from negative infinity to 0. Because we've got to have one boundary. All right. Plus 0 to infinity e to the x over 1 plus e to the 2x dx. All right. So we're going to have two limits. So here we're going to have the limit as a goes to negative infinity from a to 0 e to the x over 1 plus e to the 2x. Plus, and we're going to have from 0 to b, and this will be the limit, as b goes to infinity of e to the x over 1 plus e to 2x dx. All right. So let's find these limits. Now, what is this? Could we use a little u substitution maybe? If u is 1 plus e to the 2x, then du is going to be 2e to the 2x dx, right? Well, if this was e to the 2x, we'd be golden, we'd be good to go. But that's not going to work. But now notice something here. Notice this is a squared plus a squared. Do you kind of remember what that form kind of is? That reminds me of arctangent. So let's try a little different route. Let's let u equal e to the x. And that makes du e to the x dx. And then we can rewrite this as 1 over, let's come over here real quick. Okay, the integral of e to the x over 1 plus e to the 2x dx. Well, this is just the integral of du all over. And so this is e to the x squared, right? So that gives us 1 plus u squared. Okay, and now this is in the form of arctangent. All right, so this is the arctan of u, and u is e to the x. All right, so there we have it. We found that integral, so let's use that right here. So we have the limit as a goes to negative infinity, and we just found the antiderivative there. The antiderivative is arctan e to the x. So this is arctan e to the x from a to 0 plus the limit as b goes to infinity of arctan e to the x from 0 to b. Okay? So there we have it. Let's plug it in, or we've got our limits here. A goes to negative infinity, and we have the arctan of e to the 0 plus, or minus actually, arctan e to the a, okay, plus, come down here, limit as b goes to infinity of the arctan of e to the b minus arctan of e to the 0. Okay. Now I've got to figure out these arctans. So we have, let's do our limits here. E to the 0 is 1. The arctangent of 1, we say what angle has a tangent of 1? And that is pi over 4. Okay. So pi over 4 minus, now as a goes to negative infinity, e to the negative infinity is, what's that going to go to? Well, e to the negative infinity, let's think about that for a moment. Limit as a goes to negative infinity of e to the a. Well, that's like the same as limit as a goes to infinity of 1 over e to the a, because it's going to be a negative, right? And, well, as e to the a goes to infinity, well, this is blowing up, so this whole thing is going to 0, right? So as a goes to infinity, e to the a goes to 0. Okay, so this is going to 0. So this is going to 0, and what is the arctangent of 0? Well, we talked about in that last problem, it's 0. Okay, so that is the left-hand side. In the same way here, as b goes to infinity here, we have e to the b. E to the b is, well, this is blowing up. It's going to infinity. So as we go to infinity, what is the limit of arctangent? Again, we can think about the graph of arctangent. The graph of arctangent looks like this. It has asymptote, or 2 horizontal asymptotes, at pi over 2. Okay, so that is pi over 2. The limit as arctan of arctan as this goes to infinity is pi over 2. Okay, and again, e to the 0 is 1, and the arctan of 1 is pi over 4. So minus pi over 4. All right, what does that leave us with? Pi over 4 plus pi over 4. And that's good news there, because the left and the right side are symmetrical here. That means this side's pi over 4 and this side's pi over 4. Okay? So that is pi over 2 is our final answer. Kind of cool, huh? All right, well, there you have it. Okay, so some summary real quick here. If f is continuous on this interval a to infinity, then we're going to write that a limit like this from 0 to, or I'm sorry, from a to b, and that b is going to infinity. If we're going from negative infinity up to something, we'll just do the reverse. So we'll make it from a to b, and we'll do a limit as a goes to negative infinity. If we're going left and right, well, we need to pick a point in the middle, like we picked 0 on this last one. So we need to cut it at some point, c, and we'll do 1/2 of it is going from negative infinity to c, and then from c to infinity. Okay. Again, if either of them there, okay, in those first 2 cases there, if the improper integral converges, the limit exists. Okay. If it diverges, well, there's no limit. All right, so we have a little special theorem here. So if we have this limit here of 1 over x to the p, so this is just a power function down here, then the limit turns out to be 1 over p minus 1, all right? And we saw that back on the previous page when we did x squared. So we just did a little bit ago, we did 1 to infinity of 1 over x squared dx, and we found out that, well, according to this, so if p is greater than 1, which that is, then this is 1 over 2 minus 1, which is 1 over 1, which is 1, what we got in the beginning of the lesson there. All right? So that's going to be important because we're going to be talking about these series and sequences soon, and you'll see that come up. That's something called a geometric sequence. All right, one last situation here. Here we're not going to infinity, but we want the limit of this function here, y. And we got a problem. We have a vertical asymptote now, not a horizontal asymptote. All right, well, let's do this similar idea. We can't, it's not defined at 0. So we're going to have to make a limit again here. So let's find a limit. Okay, and we're going to make this integral from a to 1 because we can't actually evaluate it at 1. But we can see what happens when we get close to 1. All right, and we need a dx there. Should have been a dx there. So as a goes to 0, all right, and specifically is going to 0 from the right. Okay, that's what we're looking at. All right, well, that is, we can rewrite a is going to 0 from the right. Sorry, that plus is on the wrong side there. And this is the integral from a to 1 of x and negative 1/3. Okay. So we got a going to 0 plus. And so we can do that integral, I think, right? So let's add 1 to the negative 1/3. That's what we do for integrals, right? So we have x to the 2/3 and divide by 2/3 or times 3/2. And we're evaluating that from a to 1. All right. Now, we still haven't quite found our limit yet, so bring it along for the ride. Okay. And we're going to plug in 1. And so we have 1 to the 2/3 is just 1. And so we have 3/2 times 1 to the 2/3 minus, we have 3/2 a to the 2/3. Okay, well, as a goes to 0 here, well, this is just 0, right? So as a goes to 0, this goes away, and we end up with just 3/2 minus 0, which is 3/2. There it is. Sweet. Nice and simple. So the area of that is 3/2. Does that sound about right? You can always estimate it here. You know, let's make this a trapezoid, all right? Well, this has an area of 1. And this, well, this triangle right here has an area of a half, right? And so this little swoop has an area of a half? Sure. Okay? So remember, you can always go back and estimate to see if you're on the right track. Okay? Well, what if we have a vertical asymptote in the middle? We got to break it up into 2 integrals. So let's try that real quickly. So here's our graph of 1 over x cubed. Vertical asymptote in the middle here. We want to find the area from negative 1 all the way to 2. Okay, so we're going to find the area there. Okay, so let's break it into 2. So we have, this is the integral from negative 1 to 0 plus 0 to 2, 1 over x cubed dx. All right, but we can't evaluate it at 0 because it's undefined. It's got that vertical asymptote, so we need the limit. So we're going to make this from negative 1 to b. And let's crank our b coming to 0 from the left. Let's make that x to negative 3. Let's make this one, we're going from a to 2. Okay, this is the right side. Look at the picture here. A to 2. That's from here to here. And we want to know what happens if the a is becoming 0. It can't be 0. So a is going to 0 from the right. Okay. If you forget that from the right, you probably end up at the same place. But actually, it does matter here because it's negative on one side, positive on the other. So Sometimes we get away with it, but watch out. All right, so let's evaluate the integral. Let's add 1. We get x to the negative 2. Divide by negative 2. Okay, and we're going to evaluate that from negative 1 to b. And our second limit from a goes to 0 positive. Let's go ahead and evaluate that integral. And that is the same antiderivative, right? Negative x negative 2 over negative 2. And now we're going from a to 2. Okay. Well, what's going on here? All right, we may want to, rewrite this. This is the same as 1 over 2x squared, right? 1 over 2x squared, same thing. Okay, so as we think about that there, okay, we have the limit. We're going to need a little more room, so limit as b goes to 0. Okay, so when we plug in b to this fraction, we get 1 over 2b squared. 1 over 2b squared minus, plug in negative 1, we get 1 over 2. And let's add on the next one here. We've got the limit as a goes to 0 plus, and evaluated at 2. This would be 1 over 2 times 2 squared, which would be 8. Okay, minus, and plug in a, and we get 1 over 2a squared. All right. Now, what happens here when we find the limit? Well, when we find the limit here, as b goes to 0, this is going to 0. This is 1 over something really close to 0. This is blowing up. This is getting huge. It is diverging. This is going to infinity, and the 1/2 doesn't matter. Okay, so this is going to infinity on the first part, and the second part, well, you plug in 0. This again is 1 over 0, and this is going to infinity also. Okay, now, got to be careful here, okay? This is actually going to negative infinity, all right? But this diverges. That does not mean that this goes to 0, okay? Because those don't necessarily go to infinity or negative infinity at the same rate. So the fact that it doesn't converge to a discrete value, we say that this diverges, all right? So that's how we deal with that, all right? So if f is continuous on this interval and has an infinite discontinuity at b, then we can break it up like this, okay? If it's continuous on AB and has an infinite discontinuity at A, well, we can find that limit in this way as well, okay? So, and then if there's somewhere in between, like this C value like we just saw, okay, we got to break it up here. In the first two cases, it converges if the limit exists and diverges if it doesn't. In the third case, okay, if the integral on the left diverges, it diverges if either of these two parts diverges. So if either of these diverge, the whole thing diverges. That's what we just saw in that last example. All right? Diverge again means it goes to infinity. So, all right. Well, there you go. There's how you do it. Okay, so if we have an asymptote, either vertical or horizontal, we have to use limits to find the value of the integral. All right. Thanks a lot.